Hi, in this video I'm going to teach you how to compute the properties of a weld bead for a particular application by treating it as a line. This time I brought you a signal tower whose grounding is done through welding to a circular base plate as shown in the images. The welding control to be represented as a line is shown in red. The easiest way to approach to the geometric properties of this bead is by breaking it down into the basic geometries that make it up, obtaining two cases to be analyzed as shown. Notice that the sum of both inertias with respect to the same axis equals the inertia of the whole bead with respect to that axis. Now, going back to some principles, just as inertias can be added, they can be subtracted. For instance, see how the inertia subtraction of the blue rectangle from the red rectangle results in inertia of the red split rectangles on the right with respect to the fixed considered axis. Now, addressing the first case geometry, notice how it can be represented as four pairs of rectangles distributed in a circular pattern, two of them vertical and two horizontal. So, the inertia on the x-axis of this configuration will be expressed as follows. Recalling the explanation given on the subtraction of inertias, we can compute the inertia of both vertical pair of bars with respect to the x-axis as inertia of two virtually complete bars of size d, less the inertia of another pair of virtually complete bars of size d1. Keep in mind that the center of mass of both virtual rectangles of height d and d1 lay on the line of action of the x-axis. Additionally, notice how close both pairs of horizontal bars are to the axis for which we are computing the inertia. So for practical applications, we can consider those inertias to be zero. If you've seen my previous examples on how to compute the geometric properties of weld beads by treating them as lines, you'll know that you need to follow this algorithm shown in order to get the geometric properties of the welding by treating it as a line. So the linear inertia for this case is expressed as shown. I'm going to make a parenthesis here to talk about the assumption made on the null inertia for the horizontal rectangles. This assumption can be perfectly accepted by considering that in the whole process of the design of welded joints, the stress on the joint is inversely proportional to the geometric properties of the bead, such as inertia and the polar moment of inertia. This means that by assuming those horizontal bars' inertia to be zero, we're actually decreasing the value of the geometric property, thus increasing the value of the stress that will be used for the weld design. In other words, we're oversizing the design in a proportionate way such that the design is even safer. Notice that if the case was the opposite, the design stress will be lower. Thus, the welded joint could become much more risky if overloaded. Back to our welding, addressing the second case geometry, its inertia treating it as a line is shown next to its scheme. This expression is obtained from tables that already address the inertia of typical linear geometries, such as circles. You can have a look at these kind of tables in Homer Blodgett's book on the design of welds. Finally, the inertia of the whole bead treated as a line results from the sum of the inertias of its components, which is expressed as follows. If you enjoyed the video, subscribe to stay tuned on other case studies that I'll be uploading. Thanks for watching.